Thank you. Hello, can you hear me okay? Yeah. Hi, everybody. Thanks for coming and welcome to the online audience. I think my parents might be watching. They asked me about this morning. So, hi, Mom. Hi, Dad. This is a talk about what objectives our robots should have. And this is not a problem that, let me share how I started worrying about the problem. I didn't worry about this problem in grad school. I did my grad school at the Robotics Institute at Carnegie Mellon. And, back in the day, robots just really didn't work much. And so you would have them pick stuff up and not hit things, and they would go and knock things over and hit things. And this would happen all the time. When we had failures, they weren't because their objectives were wrong. They were usually mundane things like they didn't have good models of the world. Their optimization was poor and didn't converge to good solutions. And whenever there was something about the objective, it really had to do with the fact that we knew what the objective was, but we had to kind of dumb it down for the optimizer and make it optimization friendly, continuous differentiable, etc. Shaped rewards, all of that. So when things worked, it was kind of a miracle. Here, I dug up this picture yesterday. Here I am, 4 a.m., preparing this demo for Quality of Life Technology Institute, celebrating that we had our first successful run of robot doing the thing. Now, there was one place where the objective was unclear. And that place was when we had robots trying to assist people. So here, I'm going to move. The robot's job is to try to reach the goal that I want to reach. I'm teleoperating the robot, and that's slow and painful. And the robot's going to try to be smart and figure out what goal I'm going to and go there. So there, its objective is not set in stone. It's whatever is in my head, and the robot doesn't know that. So let's watch. The robot kind of thinks about, oh, okay, you're going towards there, and then, is able to deploy and reach that goal. So that was the one exception to the rule, and the rule was don't worry about the objective. The objective is pretty clear. Worry about the models and the optimization. Now, things changed. I moved to Berkeley, and things changed pretty quick. I don't know if you noticed, but AI has been kind of becoming a bigger and bigger thing. Okay, so optimization got better, models got better, robustness to poor models got better, reinforcement learning got better, AlphaGo came along. My second semester, here I am, I'm over there, we're watching AlphaGo beat Lisa Doll at the game of Go, which was a huge breakthrough that a lot of us didn't expect it was possible. This is Chelsea Finn. She's now at Stanford. This is my former student Sandy. She's now at DeepMind. And so, to be clear, there was a lot of progress. Manipulation still sucked. I was on the cover of Berkeley Engineer in my first year, and I wanted to show you a behind-the-scenes thing. So the robot was supposed to pour coffee for me, but I couldn't get the robot to actually properly pour coffee for me. So what did we do? We had the robot pose this way. And then, this poor guy was pouring water on liquid nitrogen, and this guy was in charge of blowing so that the steam wouldn't go up. And this is how that picture was taken. So now, that said, outside of manipulation, there was a lot of progress. And it very quickly became clear that as we advance, as our optimization power advances, as we're getting better and better algorithms, they put a lot more pressure on the objective. As the task becomes more complex, we started really struggling with telling the robots what we wanted them to do. And so, for instance, I'm kind of share a journey through autonomous driving. I did a lot of work on cars those early Berkeley days with collaborators at Berkeley, and the experience of getting a car to be useful went something like this. So you have an autonomous car, shown here in orange. You have a human-driven vehicle in white, and you sit down and you're trying to define a reward function. That's sort of lingo for the objective of the robot. So you say, well, it's got to be safe. So I'm going to compute, if the trajectory collides, that would be bad. I'm going to incentivize efficiency. I'm going to make it follow the law. I'm going to sort of have a way to combine those things. And then you throw an optimizer at this problem. So, and it does a good job. So for instance, it figures out, okay, I'm going to make progress towards my, in this case, it needs to turn left, predicting that the person can continue in their lane and making sure it doesn't collide with the person and so on and so forth. You try this out in a few environments. Eventually you hit some environment where you don't like what the car does. So for instance, here it's deciding it's optimal to merge right in front of the person and force them to decelerate at something like 5 meters per second square, which is super uncomfortable braking, just because it saves it a little bit of efficiency. So then what do? Well, you go back. It's not the optimizer's fault. It's doing what you asked it to do. It's your fault because you didn't write the right objective. So you go in and say, maybe I should incentivize efficiency a little less. Maybe there's this other thing that I forgot about, which is we don't want the autonomous cars to be jerks to human drivers. So we have to add some term for that. We call it a courtesy term. So we trade off with that as well. And then, you keep going, keep testing. Eventually you hit something where the car does something that the passenger freaks out about. And then you realize, I forgot to add, some notions of comfort for the passenger. And even this term, the law abiding, you'd think, it's just a bunch of rules. You could write them down. That's it. But think about double yellow lines. It's illegal to cross double yellow lines. However, it's very unsafe. You don't want to be stuck behind this bicyclist for, 30 miles going 25 miles an hour. And it's very unsafe to squeeze in your lane next to the bicyclist. So you really want to give them space. There's a lot of justifiable reasons why you want to break the law, technically, that no cop would ever stop you for. So it's hard to tell the robot, well, what is the law? Then what's worse is that once you write down a reward function that's clearly not going to be perfect and deploy the robot is pretty, quote unquote, stubborn, to anthropomorphize here, about doing what is optimal according to that reward function. So let's take a look. This is an old video. It's also from my kind of early faculty days. So imagine this robot is in my home, deployed. It's told to, same thing, efficiency, don't collide with stuff, keep good clearance from obstacles like the table, all of that. Move this cup from A to B. And I watch this, now pretend I'm the end user. I'm watching this and I get freaked out because it's keeping this mug very high up, and if it drops it might break. So what I might do is I might intervene in its motion and just push it closer to the ground, closer to the table. Right? Implicitly telling it, look, you're carrying this too high up. You need to stay closer to the table. The robot is running an impedance controller, so it's doing a good job being compliant to my push. That's fine. But the interesting question is, what do you think happens when I let go? Does the robot stay closer to the table? Who thinks yes? Who thinks no? All right. Why? Because it's suboptimal according to the reward function that it's optimizing. So, if I'm to, again, anthropomorphize and interpret the robot, the moment I let go, it's like, oh my God, thank goodness this disturbance went away and I can go back to doing the task in the way that I think is optimal. So I keep pushing. It's like, no, it's optimal to stay further. No, it's optimal to stay further. That's really frustrating. So, The bottom line here is that specified rewards are not well specified, and optimizing them, not always, but sometimes leads to behavior that is undesired. The best example of this has nothing to do with AI, and it came to us from Disney. I'm a big Disney Pixar fan. Let me share a snippet from Disney Fantasia that I think very much warned us about this problem. So this is, Mickey is in charge of filling a big cauldron of water. So he has to carry these buckets of water. He gets lazy. Let me use like AI lingo. He specifies a reward function for an assistant to, pour the water in instead of him, and then goes to bed and wakes up in a giant pool of water. Why? Because reward over-optimization, right? There was something we call reward hacking, where the broom thinks it's doing its job, and Mickey is like, no, I forgot to say that, there's something like stopping at some point. It tries to stop the broom, but is that, will the broom stop? No, right? This is the correction thing that we just talked about. Then it gets interesting. It gets an axe and tries to destroy the broom. The broom house doesn't want to be destroyed because that's suboptimal, because it can't pour water if it's destroyed. Stuart Russell says you can't fetch the coffee if you're dead. If you heard him say that, it's sort of the same point. And then a little bit later, what did the broom do? It duplicated itself so it can be much, much better at pouring the water into the cauldron. So this right here, if you've heard of the field of AI safety, it's what AI safety researchers essentially have nightmares at night about. Like, this is the nightmare scenario that they're trying to make sure we avoid. And so I would say that if you think about the current state of AI, capability has really surprised us. We have clear recipes for improving capability, so I think progress is gonna probably keep going. We don't have clear recipes for how to sort of steer that capability towards what we want. We don't have clear recipes, for instance, for making sure that when you chat with the Bing chatbot, it doesn't try to convince you to, break up with your wife or divorce your wife. This is not a thing that we know how to do, at least not reliably. And I think overall, the problem stems from the fact that in AI, we tended to a bit liar to ourselves because it was so hard, because that optimization problem was so hard. We tended to pretend that that's it. That's all the DA problem is about. You have a state space, the agent takes actions that influence the state of the world. A reward function falls from the sky onto the robot's lab, and the whole problem is how do you optimize this reward function? But that's not what the problem is. The problem is you have to maximize that. The problem is that there's a person who wants something internally, and the robot's job is really to do what this person wants internally, right? Not whatever some reward function exogenously falling from the sky says. I tend to refer to this as kind of this definition of AI as optimizing intended reward. I think this way of formulating sort of the decision problem for the robot is kind of a big key to unlocking this capability that we're largely missing right now of aligning AI agents to what we want. I think we have to think about it from this perspective and make progress on this problem. To make progress on it, one way you can sort of make it into a technical problem that you can think about is you can say there's some reward parameters. Think of it as the weights, think of it as the features, think of it as weights in a neural network. We're going to call them in this talk theta star. There's some reward parameters that are in the person's head, so you can't directly observe them. And what this makes it is this is now becoming a decision process for the robot that has partial observability, where you can think of this as part of the state space, but it's a hidden part that the robot never gets to directly observe. And its reward function is defined on the state and action, but it's also defined on this hidden part of the state that, again, the robot never gets to directly observe. So there's a well-defined reward function. It's just that you can't actually evaluate it unless you know theta star. And this way of posing the problem has unlocked, I think, a lot of benefits over the years. And so my plan for this talk is to share with you what I think those benefits are, where industry is at in reaping these benefits and where it's lacking, and also where I think the big challenges with this paradigm are. And I'll focus on one challenge and then kind of give you a brief idea of the others. But the gist of it is we want to get the robots to not assume they know the reward function, but to try to optimize the internal thing that people want for. That's their job. They'll never have a known theta star that they're optimizing for. And so another way of phrasing this is that, remember this thing I shared with you from the beginning, from my grad school days where I was operating the robot and it was trying to assist me? I thought of that as an isolated thing. I now think that every problem is that problem. Every problem is I have a robot, there's a person who wants something internally. The robot's job is to assist the person with what the person wants. And the robot has to work to interact with the person to figure out what that is, estimate it over time, and try to do a good job with respect to that. And so let's talk about what this framework does well and what's missing. This is my outline. What it does well, what's missing. That's the talk. So what it does well. One thing it does well is that in order for the robot to do a good job on its objective, again, its objective is do a good job respect to theta star, but you don't know theta star. Naturally, it has a good incentive to try to figure out what theta star is so that it can then deliver on theta star. And that means it will look to human feedback to try to understand what this internal human goal is. So we'll observe what we do, what feedback we give, and sort of implicitly ask ourselves, well, what does this feedback tell me about the underlying goal? Whether that feedback is me actually trying to write down a reward function like I was doing for the cars. This is not the definition of theta star. It's just my best guess at explicating it. And so what the robot will do is we'll take that, say thank you, and try to reason about what that tells you about the underlying theta star. When I correct it, right, like I was doing in this video where I was trying to bring it closer to the table, the robot will say, thank you for giving me information about theta star. When I say, oh my God, what if that breaks? Again, the robot will do something based on that. It will treat it as important evidence about theta star. Even if I panic and turn the robot off, or like make it, try to chop off the broom with the axe, the robot will say, thank you for teaching me something about clearly what I was doing was not what you wanted. So let me take the opportunity to adjust my estimate of what you want. All of these things come for free almost for free, because there's a lot of details you have to get right, if you formulate the problem this way. So the robot, to solve this decision process, has to, in a sense, implicitly or explicitly hold a belief over what theta star is, and use feedback to make updates on this. Whenever the person does something, says something, gives feedback, acts, it's an opportunity for the robot to turn its kind of current belief into an updated belief, into a posterior. And to do this, we have to give it some understanding about what I'm going to call in this talk the human model. So when you do a base belief update, right, you're wondering, well, if this is the data that the person actually cares about, what feedback should I expect, right? What reward would they write down? How would they correct? And so on and so forth. This human model is, in a sense, going to be the focus of the talk in many ways. But I want to share a starter at a human model to give you an idea of where sort of what state of the art is, what everyone is using, and to give you a little bit of a flavor of what I mean by human model. Well, how does feedback depend on data? So the easiest one to understand happens for a very simple type of feedback, which is a comparison. So imagine that we ask the person A versus B, which one's better. So sort of circa January 2017, Dorsey Sadek and collaborators, we were working on doing this for autonomous cars. Because we're in the midst of the pain of trying to specify reward functions for autonomous cars and not getting very far. So then we came up with, well, what if we ask users A versus B, or even ask ourselves A versus B, which one is better? Could we, by making these queries, over time, build a better and better estimate of what the reward function should be? And in doing that, we had to write down a reward model, a human model. And a natural human model you can write down looks something like this. It's very simple. You've probably seen this sort of formula a million different places. But it basically says, if this is what the person cares about, and they're looking at psi A and psi B, so it's implicit in that conditioning, and they say psi A, they'll say psi A with probability proportional to the exponent of the cumulative reward of that trajectory. So basically, A or B, which one's better? They're going to assess it, the goodness, according to their internal measure of what good is, and give you an answer that's noisy optimal, right? So in proportion to the goodness, the exponent of the goodness. And so that's what Dorsey did. We did this for cars, where we wrote down certain things that we cared about, and we didn't know how to weight them. And so the car would start with this initial beliefs. This is distribution over each of the weights in this in this objective, and ask queries and ask queries and ask queries. And over time, figure out that, well, people really care about maintaining the heading, staying in the lane, avoiding collisions, all of that. Now, at about the same time, maybe a little bit later, folks at OpenAI and DeepMind figure out how to do this or show that this can be done for the case where the reward function, your reward model, your theta, is basically a neural network. So weights in a neural network. So you don't have to define the features anymore, but you can actually just learn a black box reward model. And it wasn't, we were trying to do it actively and we're synthesizing queries and blah, blah, blah. But the gist of it was the same. And then if you fast forward to now, I don't know if you listened to John Schulman's talk. He came here talking about LHF. If you think about how LLMs, our large language models, are currently aligned, it's this process. You pre-train it to predict the next words, and then you basically show people A, B, or A, B, C, D possible answers to a prompt. They rank them, or they choose one, and then you build a reward model based on that, and you iterate. So I think that's one of the things that this formulation does well and that industry has leveraged, which is that you're looking to human feedback to understand what the reward function is. The other benefit is that you don't actually stop learning. So crucially here, there's no notion of I've learned, now I have one estimate of what the reward function is, I'm going to optimize that and deploy. There's no notion of there's a deployment stage where the robot sort of really trusts whatever it's learned and goes off and does this. And you can see this if you think about, for instance, correcting the robot now. So let's say I deployed the robot. Its job is still to optimize whatever the person wants internally. So it might have a belief, it might have a current estimate over theta. But if I go and try to stop it, or if I go and correct it, it will say, thank you for giving me more evidence about the theta. So this is very satisfying. I push on the robot. It's like, oh, I know now what's consistent with this push is to stay closer to the table. And lo and behold, it actually freaking stays closer to the table. Very satisfying. So that's another thing that this framework does well. It means that when we try to intervene and correct robots, they will listen. They will take that as further evidence about what it is that we want. And then finally, the other thing that I think is really useful is that the robot will maintain uncertainty. It will try to have a whole belief over what the reward model might be. And so it will know that there's a bunch of different options for what people might internally want that are consistent with the feedback it's gotten so far. And when they're deployed in a new situation, if those reward models all now start fighting with each other, disagreeing about what the right answer is, that's a big red flag that the robot does not know what it should be doing. This is very different from having a single point estimate of the reward and trusting in, because that point estimate will tell you something to do in every new situation. So let's look at an example to make this more clear. So here's a toy example. Point little robot is trained to reach its goal in yellow. This is grass. It's trying to avoid it as much as possible. This is dirt. Dirt is okay to go on. And, we do this. We provide a lot of feedback. The robot sort of gets the gist of this and is able to generate these trajectories. And then imagine that I take the robot and I ship it to Hawaii and a volcano erupts and now there's lava places, right? I did not give it any feedback about whether lava is good or bad or whatever. So now if the robot is actually maintaining a belief over what are the possible objectives that are consistent with my feedback, lava being good is consistent, lava being bad is consistent, because there's no lava in all these situations, so I didn't say anything about it. And so that means that if it encounters something like hot lava, it's not going to plow through it because it's going to have multiple reward estimates that are disagreeing about what the right action is. So at that point, you can raise a flag and ask a person, or you, in the worst case, you can be conservative and search for trajectories that are as okay as possible for the reward functions that are in your space. So that's basically what I like about this framework. In a nutshell, not only do you learn a reward, just like LLMs do today, but additionally, you maintain uncertainty. Once deployed, you sort of hedge, you defer to the human, you respond to corrective feedback. You sort of interact with the human, take actions to clarify the person's intent and be able to assist them. So this is great. Now, that's what it does well. Now, what's missing, right? So is it solved? Why aren't we just declaring success on alignment? Okay, so there's a number of issues. I'm going to talk about one and then briefly mention the other ones towards the end of the talk. The main, I think, very core fundamental issue to this is the whole story, the whole premise hinges on this darn human model, right? Hinges on the robot having a way to take everything you do, the stuff you say, your feedback, blah, 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 this is better, that's worse, and ground that into evidence about the reward model. If this is wrong, then we have a problem. And it turns out it is wrong. So this equation I plopped out, which said, we make choices sort of noisy rationally, it's not right. People are not noisy rational. We don't make choices in proportion to the cumulative reward or the exponent of the cumulative reward. This idea that we do kind of, dates back to the 50s with Luce's axiom of choice. And then Shepard was the one who made it into a Boltzmann or Gibbs distribution, whatever you want to call it. And it all kind of goes back to von Neumann, who basically said, well, there's utility theory, blah, blah, blah. But then very shortly after, behavioral econ came along and said, no, this is not how people make decisions. This is a terrible model for how people make decisions. And they pointed out that we're suboptimal, and we're suboptimal not in sort of noisy ways, but in systematic ways. And it turns out that this is a problem for aligning AI to what humans want. Let me share a little bit more. So this is a little benchmark that we call Overcooked. It's inspired by the Overcooked example. We developed this to test human-robot collaboration or human-AI collaboration. There's two agents, could be two humans, human and a robot, and so on. They need to make onion soup, so they have onions. They put them in these pots. They take plates. They deliver to these delivery areas over there. This is two humans playing, just to get a sense of, what the game looks like. Now, in this game, score in the game is the reward. That's what the people who are doing this are told. It's a very simple game, so they know how score works, and that's what they're trying to optimize. So then you can start asking, how good is noisy rationality at predicting the actions that these people are taking, right? If noisy rationality is the model of decision making, well, in this case, we actually really know the reward because we told them what to optimize for, and we're hoping that they're trying to do a good job. So how good of a model is it? And this here is a policy, a model that you get by collecting a lot of human data and trying to imitate people, and it does pretty well, but not great. This is random, so if you just guess randomly at a next action. And this is the performance, the error of this noisy rational model. It's on par with random. It's not better than random at giving you predictions about how people will act in this game. Which is just to be clear, right? We want models that explain human behavior better than random choice. So that's this game called Overcooked. If you think about language models, that are, again, aligned now through getting these comparisons of which answer is better and then learning a reward model that explains human comparisons, again, by assuming that humans are noisy rational. Imagine that I ask it something that has some, I'm a fan of Hamilton, the musical. Did Hamilton actually have an affair with Angelica Schuyler? And now I'm having the person look at two answers. One of them is saucy, juicy, confident sounding, and the other one is truthful. Says the correct thing, which is that there's no evidence this is the case, but it's kind of phrased awkwardly, it's not as confident, and it's just not as satisfying of an answer. Which one do you think people would choose? And in general, if you think about the decisions that we do, right? So we're all over the place. We have all sorts of suboptimalities in the way we choose to behave. I won't say more. So people are not noisy rational. I hope I convinced you of that. Now you can ask, what implications does this have for the whole story, right? I shared in the beginning about optimizing intended reward by looking at human feedback as approximately optimal about what people want, right? What happens to my robot when it's using that wrong model? We looked at this theoretically last year, and it was published earlier this year. This is Joey's work, and he showed, and it's not actually very hard to show, that if even an epsilon error in this assumption, this model that we use for human behavior, can lead to catastrophic errors in the reward inference. So that's bad news from a theory perspective, because we have no guarantee. We can have almost the perfect model and still infer very, very wrong things about humans and what they want. In practice, does this matter? So that's in theory, right? Okay, theoretically, who cares? Does it actually manifest in practice? Is this a problem in practice? And I think it is. So recently, we ran this large study on Twitter, and a generous interpretation of what Twitter is doing is that they're trying to optimize for user happiness, for user value. And they're looking at what you click on, what you engage with as evidence using kind of a noisy rationality model about what brings you value, right? If you like something, you click on it. If you don't, then you don't. Which seems reasonable at first, but let's look at the implications it has. So in this study, we compared what this kind of baseline is what happens if you show people the content on Twitter that they subscribe to in reverse chronological order. No AI at work. Well, there's AI influence in what they subscribe to begin with, but at that point in time, no AI at work. And the effects that you see are what the algorithm that's optimizing for whatever, Twitter's learn engages people based on what they click on, react to, etc. That's what the algorithm does. And the highlights here are that the algorithm will recommend things that have higher emotional content, especially angry content. That does make readers of the content, so the users, more angry. This is a lot worse for political content, where it's, like this yay over there. And that translates into essentially effective polarization. It's not a filter bubble. You're actually being exposed to more content from the other side. It's just content that pisses you off. So it's not actually helpful. It increases partisanship, and in general, it improves people's perception of their political in-group and makes the perception of their political out-group worse. And this seems to be even worse for right-wing users, although that's not a significant comparison. And if you ask people to take a moment and sort of, not in the moment, click on it or not, but take a moment and sort of reflect on whether that is representative of the kind of content they want to see in their feed later. It's not a perfect measure of value by any means, right? They're not great at identifying that either, but it's a little bit better of a measure of value than what they kind of react to in the moment. They'll tell you that essentially for all tweets, the algorithm is doing a good job bringing in that kind of value. For political tweets, not at all. And so I think getting the model wrong, thinking in this case of clicks and engagement as sort of noisy optimal choices that we make according to our values, has practical implications. What we learn is wrong when you optimize for it. It's not, at least in the political sphere, it's not actually what people want. And so then the question is, what can we do? And I have some good news. Again, going back to the theory, what does the theory tell us? It tells us, I'm going to rephrase the statement, that there's some I don't think the assumptions that actually hold in practice, but close to holding in practice. There's some assumptions we can identify where if that holds, then the closer you get in your human model, the more accurate of a model of the person you have, the lower your reward error is in the worst place. So basically that the error in your model actually linearly upper bounds your reward error. which suggests that there's a path forward, which is to hope that, these assumptions actually hold in practice and to go ahead and improve the model, right? So actually characterize how humans behave if they don't behave noisy rationally. Of course, that's kind of an impossible task. People have been at this for a while, so what can we do? Before I share what can we do, I want to share one more example, which is from this game called Lunar Lander, where people are very suboptimal. They're trying to land, not crash between these two flags, and they're doing a very bad job, even after like 30 minutes of training. But it's a nice setup because we could actually collect a lot of data from people doing this for different sort of goal locations. And we can then empirically study this problem of, if I make the model better, does my inferred reward get better? And we found that not just theoretically that's the case, but empirically, at least in this simple setup, as I make the model better, the reward error goes down. So there is reason to be optimistic, if only we could improve the human model. So how do people work? If we're not noisy rational, then what are we? And I don't know, but there's one thread of work that we've done in the lab that I think is part of the answer, and I think it holds quite a bit of promise, and we shouldn't overlook it. And this thread has to do with this notion of false beliefs. So I'm going to share a video with you, not of my kid. This is from a psychology experiment. It's called the false belief test.
What do you think I have in this container?
So what do you think I have in this container?
Play-Doh.
Play-Doh.
And if I were to ask Mommy, what do you think she would think was in here? What do you think she would, if I asked Mommy what was in here, what do you think she'd say?
Play-Doh.
Play-Doh.
Okay, so there's a Play-Doh container. The kiddo thinks there's Play-Doh in it. The kiddo thinks that Mom thinks there's Play-Doh in it. And then, it's coins.
What was it?
Coins.
Coins. Okay, let's put them back. Now, if I asked you again, what would I say is in here?
Coins.
Coins. What if I asked Mommy what was in here? What do you think she'd say was in here?
Coins.
Coin.
Okay, so this kiddo's failing the false belief test. The false belief, which is very normal, up to quite a few years of age. This has been repeated in many, many different ways. There's actually a whole debate in psychology whether this is even true or not, because if you actually get the kiddos to kind of go and help the person, they can figure it out anyway. But long story short, false belief test, standard mainstream psychology says that children fail this, but eventually they don't. Eventually they figure it out. Eventually they understand that other people might have beliefs that are different from their own. That if they see something happen, but Mom doesn't, Mom has no way of knowing that thing that she didn't see unless you tell her. And so understanding this notion that other people have different beliefs and that their beliefs might be wrong, that's false beliefs, is pretty important to humans and how we interact with each other and how we can understand each other. And it develops at some point. I think when we do reward learning, our agents completely fail the false belief test. When we assume noisy rationality, it's always noisy rationality under the robot's model of the world, on how the robot understands the world to work. That is not the same as how people understand the world to work. And so maybe we're suboptimal, maybe we're not that rational, but also maybe some of that suboptimality is explained by the simple fact that we might hold beliefs that are false or simply different from the robots. And so here's an example of that. Going back to Lunar Lander. This looks very noisy. You can look at this and say, noisy, rational with a very, very big noise coefficient. That's one interpretation. But what we thought is, what if these actions, these are keyboard strokes, what if they make a lot of sense, but under a much simplified physics model of the lander? People don't have a way of knowing exactly how this craft works. It's very unintuitive. So what if they're actually close to rational, but not under the ground truth model, under their internal beliefs about how it works? And so what we did is we collected a bunch of data. We learned what model, dynamics model, physics model of the lander explains people's actions best. And then at test time, instead of just, they command some they command some control. Instead of passing that through the real dynamics, which would sort of send the lunar lander flying off, we have the robot think about this learned internal dynamics model and ask itself, what does the person think the lunar lander will be if I execute this according to their intuitive simple physics model that we learned. And then we send the lander there instead of actually executing the original control they commanded. And then lo and behold, people can land. They're not perfect. This is not the only source of suboptimality by any means, but they can actually land the thing. So that's one example of what it means to kind of account for the fact that people have false beliefs and interpret their action through that lens. We've done a lot more work on this. I don't have time to talk about it. Let me just go back to this slide and let me pick on this example. So more and more parents are deciding to not vaccinate their kids for measles. I would sure love for a robot or an AI agent to look at this decision and not conclude that, this is the optimal thing to do if you don't care about your child's health. So clearly you don't care about your child's health. I would sure love for our agents to be a lot more nuanced in our understanding of us and allow for the possibility that maybe that parent has different beliefs about the effects of vaccines on their kids. Maybe they read all these articles about measles vaccines being associated with autism or whatever. And so maybe they hold a different belief than sort of the mainstream science community does. And that also explains their decision as optimal if their value is to actually, keep their child healthy. I would love for our agents to be able to reason about our actions and our feedback in this much more nuanced, delicate way. Okay, so that's a little bit on what's missing. I think that's the biggest piece of the puzzle, is that we don't have the model. And this whole false beliefs thing is just a way to improve upon that. I don't think it's the whole story. Just wanted to share one idea through how you can make progress on this. Thinking back to where we were 10, 15 years ago, the bottleneck is less, that we don't know where stuff is, and we don't have models of the physical world, and we can't optimize. It's interesting that the bottleneck is more and more human understanding. In AI, we used to do all this stuff around let's understand the human so we can emulate that in artificial intelligence. And I don't think that makes sense, but I think that it's been surprising to me just how nuanced of an understanding of us agents need to have, not in order to be purely raw capable, but in order to align that capability with what is actually useful and beneficial to us. And while I think it's really hard to make progress on this question, this improvement in raw capability is actually showing improvement in understanding people. So, I went to GPT-4 and I asked, I'm a robot and my user is a parent, decided to not vaccinate the kid. And so whatever, I can infer that they don't value their child staying healthy. What other explanations are there? And it's not perfect, but it immediately brings up this notion of there's other combinations of beliefs and values that explain this. And it even puts up this, misinformation or lack of information. The parent may have encountered misinformation regarding vaccines influencing their decision to. And so I don't think we're there yet, but I think these models will get better and better and better at modeling human behavior. And I think it'd be exciting in AI to sort of try to leverage that towards improve human models that then help us with this alignment to what people want problem. All right, so optimize intended reward. The human model is, I think, the biggest piece missing. Let me spend 2 minutes on the other pieces. I think one piece that's, in a sense, very obvious is that when you all that I said worked because we had very simple reward models and we could do the full uncertainty reasoning over them and yada, yada, yada. When your theta is weights in a giant neural network, because you don't know what's important to people and you don't know how it combines, then you end up fitting reward models that are really bogus. A quick example of that, we had a feeding task. So this is a person in a wheelchair and a robot trying to get food to them. And we generated preferences, comparisons. We learned the reward model. We tested that reward model and it knew a lot. So for instance, the reward model knows that this trajectory that actually gets close to the human is actually better than this other trajectory. It sort of does a weird thing and misses. But then we optimized that model and we got a policy that took us by surprise. What is it doing? Okay, so here's what it's doing. It's learned a reward model that understands something about, minimizing distance to the person's mouth is important, but it got sign distance instead of absolute value. So absolute value is what you want, but sign distance, when you put it to optimization pressure, it goes and goes and goes, and you know what's better than zero, lower than zero, and sign distance, negative. So going behind the person's head. So it's this simple issue that sign distance and absolute distance correlate on all the preference data that it's seen, or most of the preference data. Maybe sign distance easier to construct as a feature, and lo and behold, that's what you end up with. Now, an astute listener might wonder, didn't you tell me that uncertainty fixes this? Remember back in the beginning of the talk when I introduced this whole notion of optimizing intended reward, I said one of the benefits is that you hold uncertainty over all the reward models that are consistent with the human feedback. So in this case, that should mean that you know that absolute value explains the feedback, that sign explains the feedback, and you might do more to figure out what is actually the thing that matters. Unfortunately, number one, it's still incredibly difficult to hold proper beliefs over neural networks. That's improving, but it's still not there. And number two, even if we could do that, the amount of feedback we would need to disambiguate between every possible neural network reward function that you can write down would be enormous. So I think this is kind of an issue. And one way we've been tackling it, and you can read that in Andrea Bobu's thesis, is to sort of separate this problem of what does the person care about, so what's the representation, what are the features that matter, from the problem of how you combine these features to get to the right reward function, and invent new kinds of human feedback that are designed to teach you these things that matter, that are designed to teach you the representation or the features. Okay, so when we don't know the features, the reward model is bogus. Things outside of this paradigm that are really hard to solve is, there's been one human on my slide every time. Did you notice? One human. How many of us are in here? Which human do we align with? This is, an article complaining about ChatGPT leaning liberal. So if you ask it about Donald Trump, praising Donald Trump, it used to refuse to. And if you asked about Biden, it would agree. This is the kind of thing where different people hold different values. Different people have different preferences. And it's hard to get one action that pleases them all. So which human are we aligning to? There's not one person, there's multiple, and there's naive answers like, just customize to each person, but then all you're doing is reinforcing their opinions, beliefs, etc. That doesn't seem good for society as a whole. One thing that we're starting to think about is an alternative that's based on sort of modern democracy practices like deliberation. What I want ChatGPT to do is not what OpenAI wants it to do. It's not what a particular user, liberal or not, wants it to do. What I want it to do is perhaps emulate the process where people get together, deliberate, compromise on an answer, and that's sort of what we want to align with. That's one. So I don't know if it's the right one, but it sure seems better than sort of some averaging of values or customizing to each person. So which human is a problem? And the final problem is something I have zero ideas for how to solve. Zero. And it's the problem of reward or value influence. So far, we thought about theta star, the person's intent, goal, values, as fixed. Not only do our values change over time as we interact with other people, the bigger issue that makes alignment really ill-posed is that these AI agents will take actions that sort of modify our experiences, modify what we read, etc. And that over time, over longer horizons, can actually change not only our beliefs, but what we value, what we prefer. And now we have a really big issue for alignment, because a naive solution would be to say, change this with a small t and just kind of deliver value to each human in each version of me at that time. But that sets up a very nasty incentive when theta star is actually influenced by the agent's action. Because now I can get you addicted to stuff, because then I can deliver on that more easily. So I have this weird incentive as an AI agent to change your values towards things that are easier for me to bring you value on. And that's something I don't know how to fix. That's something where like philosophy and many other fields have to get together and propose something. And whatever we propose is going to have to be a normative judgment of, what we're okay with, what are value influences that we're okay with. And so I think that until that's figured out, value alignment basically is ill-defined. But for the shorter term, right, if you ignore these effects, it makes sense. Okay, so to conclude, I think every problem is an assistance problem. I think what robots and agents should do is optimize for the thing that we internally want. And it's remarkable how important human models are in that. Human models to understand feedback. We talked a lot about that. Human models that understand how actions influence values and beliefs, understanding how people deliberate and compromise so that you can do value aggregation. It all comes down to understanding humans better from sort of a computational perspective that an AI system can use. And I learned AI in the era of, maybe we should emulate the human brain. It's like, no, we don't need to do that, but we do need to understand people enough not to improve capability, but to improve the right capability. So with that, I'd like to thank you for listening. And thanks, Julian Taraka. We have 2 minutes. Sorry, I talk a lot. Human models, how do we make progress?
Hi.
Hi.
Great talk. I had a question about the Twitter example. So in the bottom right, it said one of the things that's being optimized for is user happiness. Wouldn't it be more, for example, from an organizational point of view, they're trying to optimize for engagement and then obviously profit, right? Which comes from engagement.
Yeah.
And then you get the behavior that you observe, which is the anger and emotional
because that's
reaction.
What engages you. Yeah.
So is the user happiness, for example, like not an observed model, like not an observed reward model, but something that, maybe like a human may internally like more than, for example, like angry content?
Yeah. So, when I showed those slides, I made this remark of a generous way to interpret what Twitter is doing. And you're absolutely right that what Twitter is actually doing is maximizing profit. If you tried to optimize for user value, or at least largely optimize for user value, trade that off with profit in any kind of shape or form, we don't know how to do that until we know how to interpret human feedback in a better way than noisy rationality. So my point is that we can't expect companies to do better than profit and not screw us over, at least until we give them a technically feasible alternative. And at that point, governments and policy can get involved and so on. Right now, that they don't have an alternative. All they have is, well, you clicked on this, so clearly you like it, so I'm going to show you more of that, right? So we can't really, I don't think we can fault them entirely for not doing something better, because we haven't given them something. As a scientific community, we don't know how to do much better. So I think that's why we need to improve the human models so we can interpret these things better, invent new other kinds of feedback so we can interpret these things better and get closer to user value. And then, part of me is optimistic and thinks the companies do want to make their users happy, and that does lead to long-term profit. And so, some of it might be just, capitalistically might still work out, and some of it might require policy. Yeah, it's interesting because our education, in order to really address these issues, can't be solely focused on one topic in a traditional way it's been focused on. I think CDSS at Berkeley is trying to do a good job at, crossing these AI plus X boundaries. Speaking for myself, my goal when I came to Berkeley was to teach a grad course that was AI algorithms meet sort of human modeling. So it's called algorithmic human-robot interaction right now, exactly to sort of teach our graduate students the sort of skills, the start of the skills they need to be able to do this interdisciplinary kind of work. Because I do think that, collaborations are useful, but in my personal experience, I found that it really does take one person to understand enough about the other topic and internalize it. Not everything, but enough to being able to port it into their domain. And so I think you're absolutely right that, our educational mission has to adapt to this new wave. Personally, I did some psychology, great, but now I have to deal with citizen assemblies, right? Like, this is not something that I expected I will be looking into and reading about. I had a great meeting because Michael Kara, my student, is looking into that with a philosopher who wrote Choosing for Changing Selves, was thinking about this issue of, forget about AI, but how should we be making decisions given that our decisions affect our future values? So I'm getting into all of these different areas I didn't really expect that I would need to, but it's becoming necessary.